Good morning, friends. Now we are discussing a viscous flow between two parallel plates of fluid dynamics, module number 3 of the subject fluid mechanics. So the relationship between friction coefficient and the Reynolds number for the laminar flow. So the Darcy-Weisbach equation gives here the equation of loss, head loss due to friction. So that is HF in a pipe for laminar and turbulent flow is given as 4FL V square by 2GD. So where V or U bar, so that is the average velocity. HF is the head loss due to friction. So F is the friction coefficient. So this equation, Darcy's Weisbach equation, gives the head loss due to friction in a pipe for laminar and turbulent flow. So comparing Hagen-Paisuli and Darcy-Weisbach equation. So here we have the loss of head given by Hagen-Paisuli equation is 32 mu u bar L divided by rho g d square, and for the same head loss due to friction given by Darcy-Weisbach is 4FL V square or u bar square divided by 2GD. So rearranging the terms, we have F is equal to 16 by RE, where RE is Reynolds number, that is rho u bar d divided by mu is nothing but Reynolds number. So F is equal to 16 by RE. Now consider the two parallel plates here. Two parallel plates we have taken here at a distance t apart. So the direction of flow is from left to right. The viscous fluid is flowing between the two plates. So consider a rectangular fluid element of length dx. So we are considering here a fluid element of length dx and thickness dy. So the length of the fluid element is dx and thickness is dy here. So at a distance y from the lower fixed plate. So the element is at a distance of y from the lower fixed plate. So the fluid element is at a distance of y from the lower plate. So P is the pressure intensity on the face AB. Then P plus del P by del X dx is the pressure intensity on the direction opposite to the flow. So P is pressure in the direction of flow. P plus del P by del X into dx, direction in the direction opposite to the flow. Now pressure force. So the thickness of the element is dy. We are taking 1 unit width. So the cross sectional area is now dy, that is the thickness, and 1 unit of width. So if I consider this as a rectangular element, the cross sectional area is now dy into 1. So the pressure force is now pressure P multiplied by dy into 1. So dy is the thickness, 1 is 1 unit width. So the area of this rectangle element is dy into 1. So pressure force is now pressure multiplied by area. So dy into 1. Similarly here on the face CD, the pressure force is P plus del P by del X of dx into dy into 1. So on the face CD, we have shear force on the face BC. So that is here we have shear force on the face BC. So that is nothing but stress tau is equal to shear force by area. So shear force is shear stress tau into area. So area of this bottom face is now length is dx, width is 1. So the rectangular face is now dx into 1. Similarly, on the upper face AD, we have the shear force here. So tau plus del tau by del y of dy into dx into 1. So for equilibrium, we are taking the sum of pressure and viscous forces. So here tau is due to viscosity. So on the faces BC and AD, we are taking the forces as viscous forces. Taking the summation of viscous forces in x direction and equate it to 0. So simplifying, we have here del tau by del y is equal to del p by del x. On simplifying this equation, taking the summation of all the forces shown in the figure in x direction and made equal to 0. And simplifying, we get del tau by del y is equal to del p by del x. Now velocity distribution. We have known from Newton's law of viscosity that tau is equal to mu into du by dy. So now del by, so substituting this tau as this in the equation. So that is, so expressing this tau here, whatever we get here, del tau by del y is equal to del p by del x in Newton's law of viscosity. So, and simplifying, we are getting del square u by del y square is equal to 1 by mu of del p by del x, rearranging the terms. So, by integrating the above equation with respect to y, we have this. So, by integrating again, we are getting velocity. So, using Newton's law of viscosity and this shear stress with respect to y. So we are reducing the equation for velocity. We have two constants of integration here, C1 and C2. So here C1 and C2 are integration constants. These values can be obtained from boundary equations when y is equal to 0 exactly at the plate, u is equal to 0. At y is equal to t, that is at the other plate, that is the top plate. Once again, u is equal to 0. The two extreme conditions we are taking here. So substitution of first boundary equation. So that is at y is 0. Y is made 0. So u also becomes 0. We are getting, we have C2 as 0. Substituting second boundary condition, that is y is equal to t, u is equal to 0. We are getting C1 as this. So substituting C1 and C2 in velocity equation, we are getting equation of velocity at any distance y from the bottom plate. Here u is varying with the square of y. So u is directly proportional to y square. So it is an equation of parabola. So we say that the velocity distribution across the section of parallel plates is parabolic. So the velocity distribution is shown in the figure. Thank you, friends.